welcome to the course UEC 001. In this module, we will discuss about a special type of diode, which is a Zener diode. And before that, we are going to start breakdown mechanism. So let us draw the VI characteristic of ordinary PN junction diode first. Forward bias case. So this is my diode current ID in milliamperes. This is my VD volts, and this is my forward bias region, reverse bias region, and zero potential. Obviously, this is the reverse saturation can denoted as IS. So there are two voltages. These are, suppose I am referring VBR1, breakdown voltage 1, and VBR2. So what one can observe in this particular region, as we are increasing the reverse voltage, the current will start increasing and ordinary diode will be damaged in this particular region. So this is known as the breakdown region. This is known as breakdown region. However, as far as the classification concerned, uh, two types of breakdowns are available. One is the Avalanche breakdown, and the second one is Zener breakdown. For the better understanding, I have prepared both on a same VI characteristic. So these both are actually representing my breakdowns, but in that uh, this one is Avalanche breakdown, and this is my Zener breakdown. So one can easily understand that the first thing is Zener breakdown will occur at the lower voltage in comparison to the Avalanche breakdown. So for that, for in order to occur Zener breakdown, uh, voltage requirement is low. So it occurs at low voltage, somewhere near to minus 5 volt, and this Avalanche breakdown will occur at the high voltage. So first I'm giving the key points over here so that one can easily understand and what are their requirements. So in order to have this Avalanche breakdown, there is another requirement that the doping profile of p-type and n-type semiconductor should be low. So for this doping profile of semiconductor is low. However, in case of this Zener, the doping profile, high doping profile is required. Okay, so high doping profile is required. So this is a sort of comparison also between these two, Avalanche and Zener. And another is this Avalanche breakdown occurs due to the velocity of minority carriers, due to velocity of velocity of minority carriers and their kinetic energy, their kinetic energy. However, this Zener breakdown, uh, it will occur due to strong electric field. Strong electric field occurs near the junction. Okay, near the junction. So junction of PN junction diode. So these are the couple of points by which one can differentiate avalanche breakdown and Zener breakdown. Okay, so now let us discuss the things, and a lot of things are directly clear from this picture, and these are you can check. So what is happening? The value of current increases rapidly once this breakdown occur. Okay, so you can check in this reverse bias region. We have seen that practically the flow of current will be possible due to the minority carriers. Okay, so in reverse bias, in a reverse bias case, current is possible due to the flow of minority carriers. That means one thing is clear, that as you can check, after this particular level in Avalanche and this particular level in Zener, there is a abrupt increment in the current, and which is dangerous for the ordinary diode. Like my ordinary diode will be damaged if a breakdown occurs. However, these are the special type of diodes. Those are specifically designed to be work in this particular region. Okay, and interesting point is Zener diode. We will discuss just after this mechanism. So how avalanche occur? The first thing is my doping profile of semiconductor should be low. This is the first requirement, and it will appears to the high voltage term. So the minority charge carriers, those are having some velocity, uh, and just because of their kinetic energy, they will strike the atomic structure, and the valence electrons of the atomic structure will gain this kinetic energy, and they will leave from the structure, and they participates in this particular uh, carrier generation. So the process is known as the carrier multiplication. So this process is known as the multiplication carrier multiplication, and this concept is known as impact ionization. This concept is known as impact ionization. So just because of their velocity, they will collide with the ions, and with the impact of that, uh, there will be a cumulative effect, and there is an increment in the minority carriers, and this avalanche breakdown will occur. Okay, so this is the process of avalanche breakdown. Uh, on the other side, so I'm writing just over here. This is a case of avalanche or Zener breakdown. The strong electric field near the junction of semiconductor diode will disrupt the bonding forces within the atom, which generates the charge carrier. This phenomena is known as tunneling effect, and doping profile of semiconductor is high, and you can see that in the characteristics this will be sharpened. Okay, so this particular edge is sharp. So this particular region is known as the Zener region. Okay, in fact I can write over here, this is known as Zener region, or in some literature Zener breakdown region. So there is a specific special purpose diodes designed to be work specifically in this Zener region. Okay, so this is the breakdown. Now let us discuss the Zener diode. So let's start with the symbolical representation. Anode, cathode. So again, this is my P side, this is my N side, and you can see that there is a minor variation rather than the vertical lines. Now it is having a stretched jet. Okay, so this is my uh, symbol of Zener diode. As far as the performance concern, uh, it works in three regions. So I'm summarizing. The first one is same as that we have covered in ordinary PN junction diode, forward bias mode. The second one is reverse bias mode, and the third one is the breakdown region. Okay, or it is specifically Zener breakdown region. And working of Zener diode in forward bias is same as that of ordinary PN junction diode. Also in reverse bias mode, its functionality is same, works as ordinary PN junction diode. However, in this Zener breakdown, my ordinary PN junction diode will be damaged, but this particular diode will work like a constant voltage. So my Zener diode is on in this particular region and maintain constant voltage. So this particular voltage is my VZ, which is my Zener voltage. This voltage is termed as Zener voltage, and this region is termed as Zener breakdown region, or directly Zener region. So this is my ID, this is my VD, and this is somewhere my IS value. Okay, and the current flowing in this particular region is termed as this particular current is termed as the Zener current, IZ. So there is an interesting point, and the point is voltage just before of this VZ. So there is an interesting point which is termed as PIV, and let me discuss this PIV in detail. So PIV, it is also termed as peak inverse voltage. In fact, in some literature, it is also termed as the PRV, peak reverse voltage. Now, from this characteristics, one can easily understand for an ordinary PN junction diode, we have to limit the reverse bias voltage that this breakdown can never occur. If this breakdown occurs, that means my ordinary diode will be damaged. So PIV is that particular rating. PIV ensures that my diode is in survival mode. Okay, so PIV, now let me write this definition explicitly. The definition of PIV is the maximum voltage across the PN junction diode when it is reverse bias, the maximum voltage across the PN junction diode when it is reverse bias, that can be handled by the diode safely. The maximum voltage across the diode when it is in reverse bias, which ensures the safety or security of the diode, is known as PIV, or peak inverse voltage of that diode. So this is very interesting specification. It ensures if in the reverse bias I am making my reverse bias voltage less than PIV, that means there is a guarantee of survival of ordinary P injection diode. So this rating is very, very important, and it will depends upon the manufacturer. So during your laboratory session, you must know for a particular diode what is the PIV rating of that diode. So this was my ID in terms of milliampere, VD in terms of volts. So that is the curve and forward bias, and the behavior is like this. To the anode we are connecting positive voltage, to the cathode we are giving negative voltage, and its equivalence is replaced by a battery of 0.7 volt with some diode resistance. So I'm marking 0.7 volt voltage, and resistance is RZ. And for the case if RZ is ignored, then this can be treated as zero point 0.7 volt. RZ equals to 0 ohm considered. So this is my equivalent model. So this is my equivalent model. And forward bias. Likewise, the structure in the reverse bias is now we are giving positive voltage to the cathode and negative voltage to the anode, or it will represent by an open circuit. So you can check the functionality is same as we have seen in the ordinary PN junction diode. And I'm marking this reverse bias region up to this level only. So this is forward bias, this is reverse bias, because after that this particular term is my Zener region, and this voltage is Vz, which is my Zener voltage. Functionality of diode in this Zener region will also be same, and the behavior will be like this. So my cathode is positive, anode is negative. This will be equivalent to a battery in series with a resistance. So plus minus this resistance is RZ, and this battery is now interesting. So I'm writing with different color. It is my VZ. And if this resistance is not given, then the working of Zener diode in this particular region is, here it is plus minus, and it is equivalent to a battery of value Vz, and Vz is my Zener voltage. Okay, so in breakdown region you can check it behaves like a constant voltage source of value Vz. Interesting point is at just this level. So at this level I am marking over here, this is my Iz min. So Iz min is the minimum Zener current from which the Zener region is started. So I am marking over here, it is minimum Zener current which indicates the start of Zener region. And in fact, you can check there is no limit. This curve can be moved beyond this screen, but practically there should be some limit. So I am marking here. Suppose this particular point is my IZ max, and this is my maximum Zener current. Maximum Zener current, and a term PZM, which is indicating maximum power dissipation factor. So it will be equivalent to Vz multiplied by Iz max. So the maximum power which can dissipate by a Zener diode can be represented by PZM. So this is PZM is maximum power dissipation by Zener. Okay, so you can check it is strongly depending on Iz because value of Vz is constant. You can see from the curve the value of voltage is constant. However, this current is varying from this Iz min to Iz max. So I can choose any value. Suppose this is the value of IZT. This is my testing Z current, and corresponding to this testing Z current, suppose I am having a power PZT. So my PZT should always be less than or equals to PZM. This we have to ensure for the proper functioning of a Zener diode. So for the situation, if Zener diode is working in the breakdown region, that is the Zener region, we need to check its survival. If my testing Zener power dissipation factor is less than or equals to PZM, then we can say that my Zener diode is safe. Okay. So these are the specifications also, and we have discussed their models and the VI characteristics of Zener diode. So one more parameter related. Uh, Sometimes this Zener diode have a range of PZ, that is power. Its range is from quarter watt, 1.1 by 4 watt, that is the quarter watts, to somewhere 50 watts. So if one has to calculate this quarter watt power, then PZ, I am just writing Q over here notation, quarter watt power. So it will be 4IZT, that is the testing current, multiplied by Vz. One can easily calculate by this parameter. And also there is a term which is related to the temperature. So we must understand the effect of the temperature on the performance of Zener diode. And this is very, very interesting because Zener diode is a very sensitive device in terms of the temperature. So one has to calculate the value of temperature coefficient also. So I am marking the formula for temperature coefficient. It is Tc equals to delta Vz divided by Vz whole divided by T1 minus T naught and multiplied by 100. So the result will come in percentage per degree centigrade. So this is my temperature coefficient. This is the temperature coefficient of Zener diode, where delta Vz, this is the variation in the Zener voltage. Vz is the normal Zener potential at my room temperature. T1 is the temperature of new level. T naught is my reference temperature level. And uh, general outcome is, so when Vz is less than 5 volt, then there will be a negative temperature coefficient. So Zener diode will have a positive temperature coefficient when Vz is greater than 5 volt. Application of Zener diode as a shunt voltage regulator. So if we are not having a pure DC supply at the output, then this device, Zener diode, can be used to have the fixed DC voltage at the output, provided that Zener diode is working in Zener region or in Zener breakdown region. Okay, so there are a couple of cases. So considering the first case, when Vi and RL both are fixed. So these are the two components. RL stands for load resistance over here, and Vi is input voltage when these two are fixed. Okay, so let us see the circuit first. Here R is my series resistance, this is the load resistance, input voltage Vi, and I have connected a Zener diode parallel to the load resistance. Series resistance R, internal voltage I have applied V in. This is a Zener diode of value Vz. This is my shunt voltage regulator circuit. In first case, we have seen that this quantity V in is fixed and this RL is also fixed. Now, for the analysis, the step number one, the very first step is temporarily remove this Zener diode from the circuit. Okay, so I'm redrawing the circuit by temporarily removing it. Series resistance R, my load resistance is there, input battery V in, so this is my R, and I'm saying that the voltage across the open circuited terminal is suppose V dash, and this is my RL. So now you can check uh, in this particular situation what we can observe, as both are connected in series now. That means I am saying that a current I is flowing and the same current will be my IL, as it is open circuit. So value of Iz over here is 0. Iz is 0. Now you can check these two resistances are connected in series. So from voltage division rule, one can easily calculate the value of open circuit voltage V dash. Okay, so apply. So it is V dash is nothing but voltage across RL. So it will be simply RL multiplied by input voltage divided by addition of both resistances, R plus RL. So we can easily calculate this value. Now we have to do the comparison. You can check the characteristic in this particular term. There is a two possibility: either my Zener diode is working in reverse bias region or Zener diode is working in the breakdown region. So I have to check in which particular region my Zener diode is working. In order to ensure, or in order to use this diode as a shunt voltage regulator, we must ensure that the Zener diode should work in Zener region. So this is my testing phase. So first I am doing the testing, and if V dash is greater than or equals to Vz, that means the effective voltage across this diode, if it is greater than or equals to Vz, that means my Zener is on. What it means? Means Zener diode is working in breakdown region and it will be replaced by a battery of value Vz. However, if this condition is not satisfied, if V dash is less than Vz, that means Zener is off and it is working in reverse bias region. And you can see that in reverse bias region, the functionality of Zener diode is same as that of ordinary diode. Okay, so uh, the behavior is an open circuit. So I'm writing this is A and this is B. So as I have mentioned over here the case B, so let us discuss on this case B first. So in this situation, now you can check the value of IZ equals to 0. If IZ equals to 0, what about PZ? PZ is my VZ times IZ. As IZ is 0, so this quantity will also be 0. And what about the voltage, the output voltage? Okay, voltage across the load. What is the voltage across the load in this situation? So I'm saying that this voltage is suppose my VL. So you can check VL is equals to V dash only. Okay, V, because this is my open circuit voltage. And what is the value of current IL or current I? So current I will be equals to current IL, and this is nothing but this will be V in divided by the resistance of these two. So it is simply V in divided by R plus RL. And one can easily calculate this voltage across this resistance. It is simply I into R. So this is the analysis for second case if I am assuming that my V dash is less than Vz. Means when Zener is off. Okay, so in this situation, I will not have a fixed value across the output. Okay, so let's see the analysis for case A. Okay, so now let's see the analysis for case A means if V dash is greater than or equals to Vz. Zener diode is working in the Zener region. That means it will be replaced by a battery of value Vz, and it is termed as that my Zener is on. It is termed as that is my Zener is on. So that is my series resistance. Zener is on with a battery, load resistance, supply input V in. So this is my R and this is my Vz now, and this is my load resistance R. Now I am drawing certain points. Suppose I'm saying that current flowing through this resistance is I, current flowing through this Zener is IZ, and current flowing through this load resistance is my IL, and voltage across the load resistance is suppose VL. Further, I'm saying that this is a particular node. Apply KCL at node A. What I can receive, incoming current will be equals to sum of outgoing current. That means current I will be equals to current IZ plus current IL. So current flowing through the series resistance R will be equals to IZ plus IL. What is the load voltage? VL. Now you can check over here. Zener diode is working in breakdown region. So Zener is on. That means if it is on, replaced by a battery of value Vz, and you know the fundamental concept. In parallel configuration, voltage is always same. VL will be equals to Vz, that is the Zener voltage. Now you can check the interesting outcome over here. Until unless my Zener diode is working in breakdown region, I will have a constant voltage across the load resistance VL, which will be equal to the Zener voltage. Okay, now I want to calculate this value IL, so I can easily calculate this IL current flowing through the load resistance. It is simply VL divided by RL, or now it is VZ divided by RL. And I can also calculate this current I. So easily it can be calculated. The voltage across this particular point is Vz. Okay, so voltage across resistance R is, I'm representing VR. VR is nothing but V in minus Vz. Therefore, current flowing through this resistance I will be equals to V in minus Vz divided by resistance R. Okay, and now I can easily calculate the current flowing through the Zener diode IZ from this relation. Suppose this is relation number 1. So my current IZ equals to current I minus current IL. I have already calculated these two components. Once this current IZ is known, I can calculate PZ, that is my power dissipation factor, and this is VZ multiplied by current IZ. So if PZM is given, I am saying that if suppose PZM is given, if my PZ is less than or equals to PZM, that means my diode is safe.